All right, let's look at a couple practice problems. We need to calculate the pH of a 0.035 molar solution of oxalic acid, which is H2C2O4. So to find the pH, remember, we need to use the Ka1. We can see that this is a diprotic acid. There's two H's. So let's look at our Appendix D for oxalic acid. And here we have oxalic acid, H2C2O4, and we can see the Ka1 is 5.9 times 10 to the negative 2. We're going to write that down here for a second. 5.9 times 10 to the negative 2. And then down here, the second problem we're going to do, we're going to calculate the concentration of oxalate ion. An oxalate ion is going to be the C2O4 with both of those hydrogens gone. So that means that we're going to have to find the Ka2. We're going to have to use that. So let's just look on here. Our oxalic acid. And our second one is 6.4 times 10 to the negative 5. So let's write that down too. Okay, so we've got that set up. We can put Appendix D aside. So let's look at this. Let's write what we know. We've got H2C2O4 in equilibrium. And of course, this is going to take one of our hydrogens off. So we'll have H+. And that means that we'll have our our conjugate base would be this minus one hydrogen, so just HC2O4 minus. And then let's make our ice chart here, where we were told our initial concentration was 0.035. And of course, we know that we have no of our initial product here. We know that we're going to gain. So we have plus X for our concentrations here. And of course, this will be a minus X. So we would have 0.035 minus X. All right, now let's plug in our into our equilibrium constant expression. So we have our Ka, which is 5.9 times 10 to the negative 2 is equal to our products, x times x, so I'm just going to write x squared over our, now remember, we're going to try the 5% rule, so I'm just going to put it over that 0.035 here to see if we need to use the quadratic formula or not. So we're just going to start with this to check out our math here. So let's do 5.9 times 10 to the negative 2 times 0.035. And then that's said equal to x squared. So let's square root our answer. And we would get an x value, which is equal to our H plus, right? Because x is equal to H plus here, of 0.045. Now, let's see if this makes sense. Oh, we need to have an aha moment that if I were to take this divided, so this is my x, divided by my initial concentration. So let's just try this out, but hopefully you can see our problem here. 0.045, 0.035. If I do this divided by 0.035 and times it by 100, I'm going to have well over 129% of a product being formed. Can't have that. Remember, I need this to be less than 5% if I do my x divided by my initial and then times it by 100. So we need to say, nope, the quadratic is required. So we need to back that bus up and plug in and use our 0.035 minus x. So let's set this up again. 5.9 times 10 to the negative 2 is equal to x squared over 0.035 minus x. All right, now that means that we're going to have x squared is equal to 5.9 times 10 to the negative 2 times 0.035 minus x. All right, so you need to distribute this and then subtract x squared from both sides. You can simplify that. So we would get 0 is equal to 0.002065 minus 5.9 times 10 to the negative 2 minus x squared. All right, so when we plug this into our quadratic formula, we're going to have this is equal to our a. So a is, actually, no, I'm sorry. Our a is our attached to our x squared, so negative 1. Our b is, this is a, this is b, negative 5.9 times 10 to the negative 2. And c would be, you could say 2.065 times 10 to the negative 3, or the way we wrote it out, 0.02065. It doesn't matter. So let's plug this into our calculator here. And when I put my A, negative 1, my B, negative 5.9 times 10 to the negative 2, and C, 0.002065, I get two numbers here, and one of them, obviously the negative does not make sense, so we can cross that one off. So we get that x is equal to 0.0247. Remember, our x is equal to our H concentration. So now that we have our x, again, we know that that's equal to our H plus, and we know that we can just do the negative log of 0.0247 to get, let's see what our pH is. The negative log of 0.0247, we get a pH of 1.61. All right, good calculations. So a couple of things to observe. When we're looking for pH from a polyprotic acid, it comes from the Ka1 constant. Only the first ionization contributes to the vast majority of the hydrogen ion. So we solved first without the quadratic and realized we can't use the 0.05 molar because it's larger than the initial concentration. So we had to back it up and we had to solve for the value of x, knowing that x represents the hydrogen ion. We negative log that value and pulled out the pH. So to continue this question, we carry on with the polyprotic acid here that we just found. And we're going to need to find the concentration of the oxalate ion. And to show that, we're going to take our hydrogen oxalate, HC2O4 negative, and it will release its second hydrogen ion, as well as the oxalate C2O4 2 minus ion. So let's set up this ice chart to see what we know from here. We know from the previous problem, we solved for x, and x was equal to our H plus and our HC2O4, and it was 0.0247. So we can plug that in for our initial for H plus and for the HC2O4. And initially, I don't have any of my oxalate ion. And obviously, we know that we lose our reactant, we gain product. So at equilibrium, we're going to have X, we're going to have 0.0247 plus X, and we'll have 0.0247 minus X. So now let's set up our equilibrium expression here because we know Ka2, and again, that is from our Appendix D for the second ionization energy constant. So we've got our 6.4 times 10 to the negative fifth is equal to our products. So we have 0.0247 plus X times X divided by 0.0247 minus X. So assuming that this number here for the second ionization energy is significantly smaller than the first ionization, we're allowed to toss off the X. So the X minus plus X and minus X are disregarded. Something interesting happens with the algebra, and we can do 0.0247 divided by 0.0247 is going to cancel out. And so we're left with X being the concentration. So the oxalate is the concentration of Ka2. So the very value of Ka2 becomes the value of oxalate, our oxalate ion, at equilibrium. So 6.4 times 10 to the negative fifth is equal to X, which is equal to our C2O4 2 minus concentration.